Come on, my dears, we proceed further in the theoretical part. Let us see now question number 22 about electrostatic potential energy stored in a charged capacitor. Before we go for derivation of formula of electrostatic potential energy, I would like to explain you how that energy is possessed by electric field. I am showing you. First of all, you consider parallel plate capacitor whose plates are charged with equal amounts of opposite charges. Say this having positive charge, say plus capital Q, this having negative charge, say minus capital Q. Okay, we take this plate as plate number 1, this as plate number 2. Now tell me, don't you know direction of electric field is from positively charged plate to negatively charged plate. So from left to right, its direction is this way. At present it is towards right hand side. Fine. Now I say this electric field has got some electrostatic potential energy. How can we say like that? Look, you just do one thing. In this electric field, you just put any charge. Suppose you are placing here positive charge. Tell me what will happen? This positively charged plate will repel that positive charge and this negatively charged plate will attract that positive charge. In short, on that positive charge there will be some electric force and displacement is undergone in the direction of force. So work is done on that charge. Tell me who has done that work? That electric field has done that work. And in 11th standard you had studied, if any system in any configuration has got some capacity of doing work, then it is said to be having some potential energy. Because this electric field has got some capacity of doing work in this situation, then we say it has some potential energy. We have named it as electrostatic potential energy, to be shown by symbol UE, correct? Whose formula we have to derive. Okay, fine. Now, first of all, let us find out the volume of this region in which electric field exists. The volume of this part having shape of a rectangular cube, you must remember the formula of volume of a rectangular cube. What is that? Cross sectional area multiplied by perpendicular distance between the faces at the two ends, correct? Come on. Cross sectional area means area of one plate, which is capital A, multiplied by perpendicular distance between these two parallel faces, that is small d. So what is the volume of this rectangular part of the electric field? It is A into d. Simple? Fine. Now due to this positive charge, what is the electric potential at the position of this negatively charged plate? Let it be V1, because it is the potential due to first plate. So I am giving symbol V1. Don't you know potential formula? It is electric field multiplied by perpendicular distance. But because this is the electric potential due to first plate, I should write here electric field produced by only first plate and multiplied by perpendicular distance between these two plates, which is small d. Correct? Now tell me, due to only one plate, what was the formula of electric field? E1 equals to sigma upon 2 epsilon 0. E1 equals to sigma upon 2 epsilon 0. And for a positively charged plate, direction of electric field is away from it, away from this. Correct? So that's why I am writing here E1, which is sigma upon 2 epsilon 0 into small d. And then what was the formula for electrostatic potential energy? Simply speaking, it is charge multiplied by potential. Charge multiplied by electric potential. Charge of this plate, I mean magnitude of charge of this plate, which is capital Q, multiplied by potential of this plate at this position. Correct? Electric potential developed because of this positive charge plate at this very position. Okay? And that is V1. So I am writing charge into electric potential as capital Q into V1. Capital Q as it is. What about V1? V1 formula is right now sigma upon 2 epsilon 0 into small d. Sigma upon 2 epsilon 0 into small d. Correct? This capital Q as it is. What is sigma? Surface charge density. It is nothing but magnitude of charge on either plate of a capacitor divided by its area. If this is the charge on this face, then that charge I am writing Q, and the area of the face on which that much charge is located is capital A, correct? So total charge upon total area will give you charge per unit area, which is nothing but surface charge density. So sigma is Q by A. Sigma is Q by A, correct? Rest of the terms as it is. Now 1 by 2 I am writing here. Q into Q, that is Q square. Epsilon 0 into A in the denominator. And this D which is in the numerator, I just transfer it into denominator's denominator. Denominator's denominator, correct? Fine. Now this 1 by 2 as it is. This is Q square as it is. But what is epsilon 0 A upon D? You must remember the formula of capacitance of parallel plate capacitor. C equals to epsilon 0 A upon D. So this is nothing but capacitance of parallel plate capacitor, shown by symbol C, correct? So this is one formula of electrostatic potential energy stored in the electric field between the charged plates of a capacitor, correct? Fine. Now 1 by 2 as it is. Don't you know, for a parallel plate capacitor, C equals to Q by V. Then what is Q? C into V. If Q is C into V, what will be Q square? It will be C square into V square. Q square will be C square into V square upon C, correct? Now this 1 by 2 as it is, 1 C is getting cancelled. The 1 C which is left in the numerator I am writing here, and V square as it is. Please remember this format, this formula very much, because it will be utilized at many places. UE equals to 1 by 2 CV square, 1 by 2 CV square. Now this 1 by 2 as it is, C as it is, instead of V square I just write V into V, okay? You must have come to know why I wrote like that. You know Q equals to C into V. Speak reverse, in place of C into V, we can write capital Q. So C into V is capital Q, this V as it is, 1 by 2 as it is. So which is the third formula? 1 by 2 QV. Write all the three formula combinedly. U equals to, come on, 1 by 2 Q square upon C, 1 by 2 CV square, and finally 1 by 2 Q into V. All the three formula in the single equation I have written over here. Check it. U equals to 1 by 2 Q square upon C equals to 1 by 2 CV square equals to 1 by 2 QV. Correct? Fine. This formula at present we have derived for this parallel plate capacitor and for the electric field in that capacitor. Correct? But in general, this formula is true for any electric field existing in any region. Okay? Fine. Now we go for question number 23 about electrostatic potential energy density. Electrostatic potential energy density. Fine. Shown by symbol rho E. What is that? I am showing you. What was the volume of this region in which there exists electric field? That volume was A into D. I am writing here volume, which is A into D. And in that entire volume, what was the total electrostatic potential energy stored? It was UE. Correct? Now, if in this much volume, this much is the storage of electrostatic potential energy, then what is the electrostatic potential energy per unit volume of electric field? That is what we want to find out. Then in this much volume, this is the energy. Then what is the energy in unit volume? Come on, this into this upon this. This into this, that is UE upon this upon A into D. Correct? Tell me, whenever you see any ratio, you should try to define it this way. Taking denominator 1 unit, you can just define that quantity equal to numerator. Correct? So this ratio will give me, come on, electrostatic potential energy stored in unit volume of electric field. Itself it is known as electrostatic potential energy density, shown by symbol rho E. Come on, define it. Electrostatic potential energy stored per unit volume of given electric field is called electrostatic potential energy density for that electric field shown by symbol rho E. Correct? Fine. Now tell me, this rho E I have written as it is. Now 1 upon A into D, 1 upon A into D as it is, correct? But what was the formula for UE? Come on, one of the formula was 1 by 2 CV square, 1 by 2 CV square. UE is 1 by 2 CV square, correct? Now 1 upon A into D as it is, just check it, 1 upon A into D. This 1 by 2 also as it is. What about C? C is the capacitance of parallel plate capacitor by formula epsilon 0 A upon D, epsilon 0 A upon D into V square, correct? Now this A and this A will cancel, correct? 1 by 2 epsilon 0 V square and D into D, that is D square. So it is V square upon D square. If it is V square upon D square, can't you write V upon D whole square? Yes, we can. Come on, 1 by 2 epsilon 0. What is V upon D? Come on, ratio of potential difference between two parallel charged plates of a capacitor to perpendicular distance between those two plates is going to give you strength of electric field in the capacitor. Correct? Tell me the formula E equals to V upon D. Speak reverse. In place of V upon D, I can write capital E. Correct? So this ratio gives me magnitude of electric field existing in a region between the charged plates of a capacitor. Correct? Come on, it's a square. So E square. Got it? Rho E equals to 1 by 2 epsilon 0 E square. This gives me formula for electrostatic potential energy density. Okay? This formula is also true for any electric field existing in any region. Correct? Fine. Now what about SI unit of electrostatic potential energy density? Tell me basically what is it? It is total energy upon total volume. SI unit of energy is joule. SI unit of volume is length into breadth into height, meter into meter into meter, meter cube. Correct? So joule upon meter cube is the SI unit of electrostatic potential energy density. Come on. Joule you can replace it by Newton into meter. This meter cube as it is, 1 meter will be getting cancelled. So left is Newton upon meter square, which is nothing but Pascal, capital P small a. And Pascal is the SI unit of pressure. Correct? So remember, for any sort of energy density and pressure, the SI unit is same. Not only that, dimensional formula is also same. I am showing you. Find out dimensional formula for this electrostatic potential energy density. It is dimensional formula of energy divided by that of volume. Come on, for energy, same as work, you know, m raised to 1, L raised to 2, T raised to minus 2 divided by, for volume it is L raised to 3. Simplify, m raised to 1, L raised to 2 minus 3, that is minus 1, T raised to minus 2. Correct? So remember, for energy density and for pressure, SI unit and dimensional formula, both of them are same. Okay. Let us go for now question number 24. Dielectric and its types. First of all, what do you mean by dielectric? A medium which is non-conductor of electricity is said to be dielectric. I repeat, a medium which is non-conductor or insulator of electricity is called a dielectric. Dielectric is found to be of two types. Its molecules are found to be of two types. Number one, that is non-polar. Number two, that is polar. Let us see one by one. First of all, we talk about non-polar molecules. How is the non-polar molecule of a dielectric? I am showing you. It is like this. Look, here in this molecule, the center of positive charge and center of negative charge are coinciding at the same point. So if centers of positive and negative charge are coinciding at the same point, then there is no separation between them, and then such a molecule cannot have any electric dipole moment, because electric dipole moment is given by formula by product of magnitude of either charge and this perpendicular distance between two centers of unlike charges. Now tell me, here the centers of unlike charges are superposing on each other, so there is no separation between them, and when this separation is 0, naturally this product will be 0, correct? So remember, non-polar molecule is that which does not have any electric dipole moment, but mind well, when in the absence of externally applied electric field. If a molecule does not have any electric dipole moment in the absence of externally applied electric field, it must be non-polar. Got it? Fine. What will happen in the presence of externally applied electric field? I am showing you. Consider the electric field existing between charged plates of a capacitor. Now, in this applied electric field, I just place some non-polar molecule like this, correct? But now tell me, there is a center of positive charge, there is a center of negative charge. On both the centers, what this electric field will do? Will provide electric force. You know, the direction of electric force exerted by electric field on the positive charge is in the direction of the field, but direction of electric force exerted on negative charge is just opposite to electric field. So positive center of positive charge will shift this way in the direction of externally applied electric field, and center of negative charge will shift in a direction opposite to applied electric field. I mean to say, if center of positive charge moves little bit this way, center of negative charge moves little bit this way, then there will be some separation between those centers, correct? That separation is suppose small d, which is right now not 0. Earlier it was 0, now it is not 0. Neither q is 0 nor d is 0. In short, p is not 0. Meaning thereby, this dipole or this molecule has got some dipole moment, correct? Because there are two poles, negative and positive, we call it dipole, and it has got some dipole moment which is not 0. But mind well, this electric dipole moment is known as induced electric dipole moment. Why it is called induced electric dipole moment? Because in the absence of externally applied electric field, it had no dipole moment. Right now it has dipole moment because of presence of externally applied electric field. So it is that dipole moment which has been inspired, which has been induced by some external agency, and that's why we call it induced electric dipole moment. What about induced electric dipole moment of this dipole? It is P equals to Q into D, which is right now not 0. So remember, every non-polar molecule acquires some induced electric dipole moment in the presence of properly applied electric field. Got it? Let us see now what is called polarization. A phenomenon in which whenever any non-polar molecule is subjected to some external electric field, there is some separation prepared, developed between the centers of unlike charges. This very phenomenon is known as polarization. I repeat, a phenomenon in which whenever any non-polar molecule is subjected to some externally applied electric field, there is some separation between the centers of unlike charges. This very phenomenon is known as polarization. And because of polarization, such molecules now acquire some induced electric dipole moment. Okay, fine. Practically, we find that this induced electric dipole moment is found to be directly proportional to externally applied electric field if it is not very strong. Okay? When this is proportional to this, why don't you remove this sign of proportionality? Then we have to place proportionality constant as alpha. What is alpha? It is called polarizability of a given molecule. I have written here polarizability of a given molecule. Correct? Fine. Now what about magnitude on both the sides? If you take it, then P equals to alpha into E0. P equals to alpha into E0. Find out alpha, it will be P upon E0. Correct? In textbook, the definition of alpha is not given. We can just give it from here, very simple. Induced electric dipole moment obtained in a given molecule per application of 1 unit of external electric field is called its polarizability. I repeat, induced electric dipole moment obtained in a given molecule per application of unit external electric field is called its polarizability, shown by symbol alpha. Simple? Fine. What about SI unit? SI unit of this will be ratio of SI units of these two. For electric dipole moment, don't you know, it is coulomb into meter. Here it is, coulomb into meter. Divided by, for electric field, it is Newton upon coulomb. Newton upon coulomb. Now this coulomb will go up, coulomb into coulomb, that is coulomb square into meter upon Newton. Correct? What about dimensional formula? Very simple. Dimensional formula of alpha, so I just put it in such a bracket. And now, you know, for charge, it is a raised to 1, t raised to 1, but it's a square. So a raised to 2, t raised to 2, a raised to 2, t raised to 2. For length, come on, L raised to 1, and Newton, that is for force, m raised to 1, L raised to 1, t raised to minus 2. Here it is, m raised to 1, L raised to 1, t raised to minus 2. Simplify, m raised to 1 will go up, m raised to minus 1, then L raised to 1 from numerator and from denominator will get cancelled, and t raised to 2 plus 2, that is t raised to 4, a raised to 2 as it is. Okay, fine. What are the examples of this non-polar dielectric? Examples are hydrogen, nitrogen, oxygen, carbon dioxide, methane, CH4, ethane, that is C2H6. Okay, these molecules are the examples of non-polar molecules. Okay. What about polar dielectric? Polar dielectric has molecules which possess electric dipole moment even in the absence of externally applied electric field. I am showing those molecules. They are like this. In each molecule, you can see there is some separation between the centers of negative and positive charge, meaning thereby each molecule has some electric dipole moment even in the absence of externally applied electric field. Okay? Each molecule which behaves like molecular or atomic dipole has some electric dipole moment, but if you think of entire dielectric medium, then its total electric dipole moment is 0. Why it is 0? Because when you think of dielectric medium, which is polar dielectric, in that there is a very large number of atomic dipoles, and those atomic dipoles are arranged in 3 dimensions in all the directions with uniform number, and that's why they just cancel out their dipole moment vectors, and that's why the total electric dipole moment would come out to be 0. Correct? So resultant electric dipole moment produced out of entire dielectric medium is 0 vector. Correct? Fine. And here in this figure, I have shown few molecules which cancel out their dipole moment vectors. How? I am showing you. Whatever is this electric dipole moment vector in this direction, here is electric dipole moment which is just in opposite direction with the same magnitude. So these two will cancel out. Similarly, these two. Whatever is dipole moment towards right hand side, same is the dipole moment towards left hand side. So these two will cancel out. Whatever this is the dipole moment in vertically upper direction, same is there vertically downward direction. Correct? So these two also will cancel out. So this is how in a dielectric medium there is a very large number of atomic dipoles, and they are arranged in 3 dimensions in all the directions with uniform number. That's why the total electric dipole moment produced out of entire dielectric would be 0. Correct? Fine. Come on, my dears. Now let us see some of the examples of polar molecules. They are HCl, H2O. These 2 examples they have given in the textbook. Let me give you some other examples. Come on, H2S, that is hydrogen sulfide, SO2, that is sulfur dioxide, N2O, that is nitrous oxide, and NH3, that is ammonia, correct? These are those molecules which are called polar molecules. They have some electric dipole moment even in the absence of externally applied electric field. Okay, fine. Now let us see what will happen in the presence of externally applied electric field. I am showing you. Now between the charged plates of a capacitor, I just introduce some dielectric medium. Okay, might be polar, might be non-polar. If it is non-polar, then in the presence of externally applied electric field, some dipole moment will get induced. If it is polar, it must be having some dipole moment right from beginning, correct? But initially when you place that dielectric medium here, it so happens there are atomic dipoles which are randomly arranged. Then on each dipole, the externally applied electric field will exert some torque. Remember the formula which we had derived in chapter number 1, vector tau equals to vector P cross vector E. Vector tau equals to vector P cross vector E. So on each atomic dipole, the externally applied electric field will exert some torque. How long that torque will be exerted? Till the electric field will make an effort to make the dipole very much parallel to it, correct? So electric field will constantly apply the torque till the electric dipoles become very much parallel to externally applied electric field. But at room temperature, the atomic dipoles undergo some thermal vibrations, correct? So because of their own some average kinetic energy, they simply do not get aligned very much parallel to externally applied electric field. They make small angles with the externally applied electric field. I am showing you. Some dipoles may get aligned whose kinetic energy is less, and some other dipoles whose kinetic energy is more, they may not get aligned very much parallel to applied electric field, correct? They may make some little small angles with the electric field. Fine. So this is the situation at room temperature. Okay. For any electric dipole, if it is remaining stationary, that is, it is under equilibrium, then for that dipole it has so happened that its average kinetic energy is just equal to modulus of electric potential energy. Look, under equilibrium condition, the dipole will remain steady, then at that time these two energies have become equal. What is average kinetic energy? As you studied in 11th standard, average kinetic energy per one molecule is 3/2 kT, where small k is Boltzmann's constant. What is the value? It is not required here, but just recall 1.38 into 10 raised to minus 23 joule upon molecule into Kelvin, correct? And what about capital D? It is absolute temperature, and modulus of capital U, that is modulus of electric potential energy of electric dipole in externally applied electric field, is modulus of minus of vector P dot vector E. Because it is attached with negative sign, I just take modulus here, correct? Because this term is every time positive, then this term also has to be positive. That's why I am taking modulus, correct? Modulus of minus of vector P dot vector E. Okay? When these two energies have become equal for any dipole, the dipole will remain steady. It is said to be under equilibrium, correct? When kinetic energy will be more than this potential energy, then it will start performing thermal oscillations. Got it? Now, if you want that this dipole should be aligned more and more parallel to applied electric field, if you want more and more parallel alignment, then you can do two things at a time. You can increase the strength of externally applied electric field, and at the same time you can decrease the temperature. When you increase the intensity of applied electric field and when you decrease the temperature, what will happen? These dipoles get more and more aligned parallel to this electric field, correct? The angle between vector P and vector E goes on decreasing. More and more dipoles start getting aligned parallel to applied electric field. But if you want that all the atomic dipoles must be compulsorily perfectly parallel to applied electric field, then you must take that condition as an ideal condition, because it is not obtained so in practice. It is called ideal condition, and that ideal condition is obtained theoretically speaking at absolute zero temperature, which is theoretically possible lowest temperature. Okay? And that absolute temperature is T equal to 0 Kelvin. We call it absolute zero temperature. At absolute zero temperature, all these atomic dipoles, they do not have any thermal kinetic energy, and then they will be getting aligned perfectly parallel to applied electric field. Correct? Now onwards, in all the theoretical topics later on in this chapter, we are going to consider such ideal condition in which all the dipole moment vectors are parallel to applied electric field. Fine. For each molecular dipole, I have written here vector P is now very much parallel to externally applied electric field, but when at absolute zero temperature, and that condition is called ideal condition. Okay? Now onwards we will consider only ideal condition. Okay? Now my dears, we go for question number 25. Question number 25 about resultant electric field in dielectric capacitor. You must have remembered what is called dielectric capacitor. A capacitor in which there is some dielectric medium introduced in the region between the parallel plates is called parallel plate dielectric capacitor. Okay? But now question arises, how much is the resultant electric field inside that dielectric medium? Let us find out. Consider parallel plate dielectric capacitor whose positively charged plate is this, negatively charged plate is this, and the perpendicular separation between the parallel plates is small d. Fine. Now tell me, here in the region between these two unlikely charged plates, there is an electric field from positively charged plate to negatively charged plate. From positive to negative. So the direction of that electric field I am showing this way, from positive to negative. Correct? Let it be E0. Why symbol is E0? Because we are talking about that electric field when there is no dielectric medium here, or you can say when there is vacuum. Whenever there is a vacuum or free space, at that time the strength of electric field is shown by symbol E0. And what is the formula for that? It is sigma upon epsilon 0. Sigma upon epsilon 0. Remembered? In case of capacitor, remembered? The electric field produced by positively charged plate, it was, come on, from positive to negative, it was having magnitude sigma upon 2 epsilon 0. Similarly, electric field produced by negatively charged plate was also in the same direction with the same magnitude. So ultimately, resultant electric field between the charged plates of a capacitor was sigma upon 2 epsilon 0 plus sigma upon 2 epsilon 0. Altogether it was sigma upon epsilon 0. Here it is, sigma upon epsilon 0. But as per textbook, I have shown the symbol sigma f. You know the reason which they have given in textbook for showing that symbol like sigma f. They have given the reason that f stands for free. F stands for free. That is true. But you know what reason have they given? That if you connect here a battery of low voltage, naturally you will have low value of this surface charge density. And if you connect a battery of higher terminal voltage, you will have higher value of this surface charge density. So what the reason they have written? That because we are quite free to select any value of sigma, then we write sigma f, f for free. My dears, it is not correct reason. Correct reason is that when you change the terminal voltage of the battery which is connected across these two plates, at that time these charges are getting displaced on this surface. Correct? The surface charge density changes because of movement, because of displacement of those charges. So because these are those charges which can move freely on the surface of this plate, that's why we write f. F stands for free, but it is because of free movement of these charges. These charges are not bound charges, they are free charges. That's why this surface charge density produced by free charges is called free surface charge density, shown by symbol sigma f. F stands for free movement of these charges, correct? Fine. It is from positive to negative charge plate towards right hand side. In this case, I have shown by symbol E0, correct? But now what we do? We just introduce some dielectric medium in this entire volume between these parallel plates. Okay. What is the volume of the dielectric medium? Let us find out. Volume. Volume of this dielectric slab means volume of rectangular part like this. In this region, we just replace it by dielectric medium. So what was that volume? Remember, volume was A into D, correct? Cross section area multiplied by length. Cross section area is A, this much length is small d. Fine. Now what will happen? In this dielectric medium, there are atomic dipoles, correct? If it is polar dielectric, each atomic dipole will have electric dipole moment right from beginning. If it is non-polar, then some induced electric dipole moment will be there, correct? Because already we have applied this external electric field. Fine. But now on those atomic dipoles, what this externally applied electric field will do? Will exert torque. How long? Till they get steady, till they become stationary, correct? But that sort of equilibrium condition is established. At that time, the dipoles may make some small angles with applied electric field. But in the figure, I have shown all the dipole moment vectors perfectly parallel to this applied electric field. But you know that sort of situation is called ideal condition, and that ideal condition we can have only at one temperature. What was that? Absolute zero temperature, correct? So this is the situation which we can get at absolute zero temperature, which we have considered right now. Okay, fine. So just to show all these dipole moments, come on, very much parallel to this applied electric field. Fine. All the dipoles have been aligned perfectly parallel in the direction of applied electric field. Now, in this condition, you can see the charges deposited on this left face of dielectric medium. They are all negative, which is the polarity opposite to this positive charge, correct? And here, polarity of charge accumulated on this face of dielectric medium is opposite to polarity of this negative charge, correct? I mean to say, the polarities of electric charges on the surface of dielectric medium and on the surface of oppositely connected plate of a capacitor are opposite. Here positive charge, then here negative charges. Here negative charge, then here positive charges. Correct? Fine. And now tell me, if somebody is asking you, what is the total free charge on one plate of a capacitor? In case of surface charge distribution, what is the formula for charge? It is surface charge density multiplied by area. Here QF, then here you should write sigma F into area is A. Similarly, if somebody is asking you what is total bound charge here, see these charges, which remain very much bound with the surface, they are called bound charges. They are not free charges, they are bound charges. That's why I am writing symbol QB, B for bound, B for bound, F for free, B for bound. In case of surface charge distribution, what is the formula for charge? Surface charge density multiplied by area. And surface charge density for bound charges I am showing by symbol sigma B into area. Area of this face is same as area of this plate. Let it be capital A. Simple? Fine. Now tell me, here is accumulation of negative bound charges. Here is accumulation of positive bound charges. And electric dipole moment is from negative to positive. Now I would like to find out total induced electric dipole moment in the entire dielectric medium. Come on, because all the vectors are in the same direction, you can add them like scalars. And then finally, the total induced electric dipole moment in the entire dielectric slab, I am showing by symbol PT, T for total, correct? What is the formula for electric dipole moment? Product of magnitude of either charge and perpendicular distance between opposite or unlike charges, correct? Come on. If I want total induced electric dipole moment, then I should express it by such a product of total bound charge on either face multiplied by perpendicular separation between two opposite bound charges, correct? Come on. Bound charge on one face of dielectric medium is QB. So I am writing QB multiplied by perpendicular distance between this unlikely charged by bound charges. These surfaces are having unlike charges. This is having negative bound charge. This is having positive bound charge. What is the perpendicular separation between these two faces? It is small d. So I just multiply by small d, correct? Magnitude of either charge multiplied by perpendicular distance between opposite charges is called electric dipole moment. And because I am finding for entire slab, I just write PT, T for total, correct? What is QB? QB is right now sigma B into A. QB is sigma B into A into small d as it is, correct? Now we define one more physical quantity called intensity of polarization. Intensity of polarization shown by symbol capital P. Now how is it defined? I am showing you. Just transfer this A into D in the denominator of this term, okay? So I am writing PT upon A into D, PT upon A into D, correct? Tell me, what was PT? Total induced electric dipole moment. Here it is. Total induced electric dipole moment, correct? What about A into D? A into D is nothing but total volume of dielectric medium, correct? So when I divide this by this, what will I get? Induced electric dipole moment per unit volume of dielectric medium. The same ratio is known as intensity of polarization obtained in that dielectric medium, shown by symbol capital P. Come on, define it for the last time. Induced electric dipole moment obtained in a given dielectric medium per unit volume of it is called intensity of polarization obtained in that medium, shown by symbol capital P. Come on. If you find out PT upon A into D from here, PT upon A into D, then it will be, when you transfer this A into D in the denominator, what is left out here? Sigma B. But what was sigma B? Sigma B was known as bound surface charge density or surface charge density of bound charges. Surface charge density of bound charges. And tell me, if you find out the unit of P, it will be unit of sigma B. What is sigma B? Bound surface charge density. Any surface charge density has the SI unit coulomb upon meter square. Coulomb upon meter square. So if SI unit of this is coulomb upon meter square, for this also it will be coulomb upon meter square. Here it is. Unit will be, come on, coulomb upon meter square. Got it? Now tell me, here there is induction of positive bound charges on this face of dielectric medium. Here there is induction of negative bound charges on this face. And don't you know, direction of electric field is from positive to negative, from this positive to this negative. So direction of electric field developed inside the dielectric medium due to bound charges will be from this positive to this negative. It is in this direction. Come on, shown by symbol EB. B for bound. B for bound. Correct? Now tell me, this direction is opposite to this. So now if somebody is asking you, what is resultant electric field in this dielectric medium? Let it be capital E. Then that resultant, because these two vectors are in opposite direction, I can just find out bigger minus smaller. Bigger minus smaller. This is bigger, so E0. This is smaller, minus EB. Bigger minus smaller will give you resultant electric field in the dielectric medium, whose direction will be same as direction of bigger electric field. Bigger electric field is right now towards right hand side. Then this resultant electric field is also towards right hand side. Correct? Come on. E equals to E0 minus EB equals to E0 minus EB. Correct? What is E0 formula? E0 formula is sigma F upon epsilon 0. E0 is sigma F upon epsilon 0. The way you wrote for E0, we can write for EB. Come on, instead of sigma F, you may write sigma B. Okay? So what is formula of EB? Sigma B upon epsilon 0. Come on, sigma B upon epsilon 0. Here it is. Come on, E0 is sigma F upon epsilon 0. minus EB is sigma B upon epsilon 0. Take epsilon 0 in the LCM, then in the numerator it will be sigma F minus sigma B. Fine. Now transfer this epsilon 0 here. When you transfer this over here, it is epsilon 0 into E, and that will be sigma F minus sigma B. Sigma F minus sigma B. Correct? Now this epsilon 0 into capital E as it is. What is sigma F from here? Sigma F will be epsilon 0 into E0. Epsilon 0 into E0. Write it here. Sigma F is epsilon 0 into E0 minus sigma B. Sigma B is nothing but capital P, which is the intensity of polarization. So sigma B I just replaced by capital P. Give it equation number 1. Take care while putting symbol of electric field. If it is E0, you must write E0 only. Okay. If it is E, then you must write E only. Don't change the symbol. Okay. Now what is called linear dielectric? Linear dielectric is that in which the intensity of polarization is found to be directly proportional to resultant electric field. Such a dielectric is called linear dielectric because when there is a linear or direct proportionality relation, at that time graph of this versus this will be a straight line graph, and that's why, because the graph is linear, we call the relationship to be linear, and hence the name linear dielectric. I repeat, a dielectric in which intensity of polarization is directly proportional to strength of resultant electric field inside it is called linear dielectric. When P is proportional to E, you can say that dielectric is linear dielectric. Okay. Remove sign of proportionality and put some proportionality constant. Normally we place proportionality constant in terms of single constant, but here for a specific purpose we have to write as a multiplication of two constants. Which are those two constants? One is epsilon 0, which you know very well. It is called permittivity of vacuum. What is the value? 8.85 into 10 raised to minus 12 Coulomb square upon Newton meter square. What is another constant? It is shown by such a symbol, chi E. You have to write it like that. You have to write like this. And what about pronunciation? Pronunciation is chi E. The spelling is C-H-I, chi, chi E. And it is called electric susceptibility. Electric susceptibility. Electric susceptibility of a given dielectric medium. For different dielectric media at different temperatures, their electric susceptibility value will be different. The value of electric susceptibility for a given dielectric medium, it depends on temperature. Correct? In general, you can say its value depends on two factors, type of dielectric medium and on temperature. Okay. Why we write proportionality constant in terms of product of two constants? Just to make this chi E unitless. So with the purpose of making chi E unitless, we write this right hand side proportionality constant as epsilon 0 into chi E. Then let us prove that chi E, if it is expressed this way, it will be unitless. I am showing you. What is chi E from here? Just transfer epsilon 0 into capital E in the denominator of P. So it is P upon epsilon 0 E. Correct? What about SI unit? For this is not electric dipole moment, mind well, this is intensity of polarization, and intensity of polarization is nothing but sigma B, which is bound surface charge density, which had the unit Coulomb upon meter square. Write that unit here, Coulomb upon meter square. What about epsilon 0 unit? Coulomb square upon Newton meter square. Coulomb square upon Newton meter square. What about SI unit of electric field? It is Newton upon Coulomb. Now tell me, Newton getting cancelled, meter square also getting cancelled, 1c is getting cancelled, and the 1c which is left here will be getting cancelled with this c. Ultimately everything is getting cancelled from right hand side. So you can say chi E is unitless, and because it is unitless, it has to be dimensionless. Any physical quantity which is unitless, it has to be dimensionless. But reverse may not be true in some cases. For example, plane angle. Plane angle is dimensionless, but it is not unitless. It has the unit SI unit radian, correct? So if any physical quantity is dimensionless, it need not be unitless. It may be unitless, may not be unitless, okay? But if any physical quantity is unitless, it will be certainly dimensionless, okay? Now, from equation 1, just put up the value of P from in equation number 1. Come on, start here. Epsilon 0 into capital E. Here it is. Epsilon 0 into capital E. That equals to epsilon 0 E0. Epsilon 0 E0 minus as it is. What about capital P? Intensity of polarization obtained from here. Come on, P is how much? Epsilon 0 chi E into capital E. Epsilon 0 chi E into capital E. Epsilon 0 chi E into capital E. Correct? Now transfer this term over here. From minus it will become plus. And then you can take epsilon 0 into E as common. Epsilon 0 into E is taken common. Then left inside the bracket from here it is 1 and plus left inside the bracket from here will be chi E. I just repeat it. Epsilon 0 into 1 into E. It is epsilon 0 E. Correct? Now multiply this, this and this. Epsilon 0 chi E into capital E. When you transfer this term over here, from minus it will become plus. Epsilon 0 chi E into capital E. Epsilon 0 chi E into capital E. Simple. What is left on the right hand side? Epsilon 0 E0. Epsilon 0 E0. Give it equation number 2. But now, in this left hand side, the product of this and this, that is epsilon 0 into 1 plus chi E. Epsilon 0 into 1 plus chi E is renamed as permittivity of given dielectric medium, shown by symbol only epsilon. If it is permittivity of vacuum, you may write epsilon 0. But if it is permittivity of given dielectric medium, you should write simply epsilon. Okay? Come on. Replace this term by epsilon. Replace this term by epsilon. Here, when you write here epsilon, it will appear epsilon into capital E. Epsilon into capital E. And that equals to epsilon 0 E0. Epsilon 0 E0. Correct? Now, find out capital E from here. Then you can transfer this epsilon in the denominator. So it is epsilon 0 E0 upon epsilon. Epsilon 0 E0 upon epsilon. And now, this epsilon 0 you can transfer into denominator's denominator. Into denominator's denominator. So here epsilon as it is, and this epsilon 0 I just transfer in the denominator's denominator. But don't you know, ratio of permittivity of given dielectric medium to the permittivity of vacuum is called dielectric constant of that dielectric medium, or it is also called sometimes relative permittivity, shown by symbol epsilon r, or normally shown by symbol capital K, which is dielectric constant. So replace this ratio by dielectric constant. So what is the result ultimately you have obtained? E equals to E0 upon K. E equals to E0 upon K. Please remember this result in words like this. If a free space having electric field E0 is replaced by dielectric medium having dielectric constant K, then the resultant electric field in that dielectric medium becomes kth part of E0 or becomes 1 upon K times E0. I repeat, when a region of free space having electric field E0 is replaced by dielectric medium having dielectric constant capital K, then the resultant electric field obtained in that dielectric medium is found to be kth part of E0 or 1 upon K times E0. Okay? And tell me, value of K for every dielectric medium is certainly greater than 1. For every dielectric medium, if value of K is greater than 1, then E will be less than E0. E will be less than E0. Okay? Fine. And have you remembered? I told you for metal, the dielectric constant is infinite. Why it is infinite? I am showing you. Find out K from here. Find out K from here. It will be E0 upon E. K equals to E0 upon E. Correct? Tell me, did we understand one fact in this chapter? Whenever you just expose any metal to some external electric field, what happens? Inside the metal, there is externally applied electric field and there is also induced electric field, which are equal in magnitude, opposite in direction. So they were cancelling each other, and so you did not have any resultant electric field inside the metal. So remember, for any metal, there is no resultant electric field inside the metal, so E is 0. For every metal, E is 0. When E is 0, something upon 0 will be infinity. That's why K will be infinity for metals. Okay? For good conductor, for metal, remember dielectric constant is infinity. Okay. Now from equation number 3, just take this epsilon 0 in the denominator of epsilon. So it will be epsilon upon epsilon 0. Epsilon upon epsilon 0. It will be 1 plus chi e. Here it is. 1 plus chi e. But tell me, such a ratio is nothing but dielectric constant of given dielectric medium shown by symbol capital K. Right hand side 1 plus chi e as it is. You know chi e is unitless, so K is also unitless. Okay. Remember this relationship between dielectric constant and electric susceptibility. Okay. Now we define one vector field. What is that vector field? It is called electric displacement, shown by symbol vector D. How is it defined? By vector addition of these two vector functions. One is epsilon 0 vector E plus another is vector P. Let me identify. Come on, what is epsilon 0? Permittivity of vacuum. What is vector capital E? Resultant electric field in a given dielectric medium. And vector capital P is intensity of polarization obtained in that dielectric medium. Correct? So an addition of, or you can say resultant field obtained out of epsilon 0 vector E and vector P is called electric displacement vector function. Correct? Shown by symbol vector capital D. What about its SI unit? SI unit of this means SI unit of this, and SI unit of P. SI unit of P is SI unit of sigma B. For surface charge density, it was coulomb upon meter square. Correct? So whatever is the unit of this, which is coulomb upon meter square, will be unit of this. So unit of electric displacement, remember SI unit coulomb upon meter square. Okay? And why we define vector D like this? If you do so, then you can express all the results of electric field very easily. In order to express majority of results obtained in electricity very easily, we just define this electric displacement vector function like this. Okay? Then one very important result, Gauss law in the presence of dielectric medium. In the textbook, at the end of the chapter, they have written this format of Gauss law to be utilized in dielectric medium. What is that format? Closed surface integration of electric displacement in a given dielectric medium is equal to the charge enclosed, free charge enclosed by that closed surface. I repeat, what is Gauss law for dielectric medium? I am just speaking the statement. Look, closed surface integration of electric displacement vector function taken over the closed surface inside the dielectric medium is equal to the amount of free charge enclosed by that closed surface. Remember, here Q is not the bound charge, it is free charge, but certainly it should be enclosed by considered closed surface. Okay? Now you may have question that why this is equal to this, correct? Let me prove. Nobody will ask you for the proof. I am just showing you for your mental satisfaction. Okay? Look here. Tell me what format of Gauss law you have remembered. Gauss law simply states that the electric flux linked with any closed surface is just equal to ratio of charge enclosed by that closed surface to permittivity of given medium. But right now you are talking about dielectric, whose permittivity we have shown by symbol epsilon. Correct? So don't write here epsilon 0, you must write epsilon, because you are talking about Gauss law not for vacuum, for dielectric medium. Fine. This is the charge enclosed, but it should be free charge, it is not the bound charge. Okay? And here, how this is equal to this, I am showing you. Come on, this is the format which you have remembered. Instead of vector dA, normally we write here vector dA. Vector dA or vector ds, they both have same meaning. They are called surface area vector. Correct? So you may write here vector dA, you may write vector ds. No problem. Come on. Transfer this epsilon over here. Correct? When you transfer this epsilon over here, it is epsilon into vector E dot vector ds, and that equals to Q. Now tell me, this closed surface integration as it is, instead of epsilon vector E, come on, When you write here vector sign, here also you may write vector sign. So epsilon vector E will be epsilon 0 into vector E0. Epsilon vector E is nothing but epsilon 0 into vector E0 dot vector ds, and that equals to q. Now tell me, what is epsilon 0 vector E0 from here? Epsilon 0 into vector E0 from here, transfer this, will become plus here. So epsilon 0 into vector E0, when you write here vector sign, here also you must write, here also you must write, correct? So epsilon 0 vector E0 will be epsilon 0 into vector E plus vector P. Here it is, epsilon 0 into vector E plus vector P. Okay, I repeat for the last time, epsilon 0 vector E0 find out from here. Make subject of the equation this term, then you transfer here, then epsilon 0 into vector 0 will be epsilon 0 into vector E plus vector P, epsilon 0 into vector E plus vector P dot vector ds, that equals to q. But tell me, how did you define electric displacement vector function? Like this, by symbol vector capital D. What was that? Epsilon 0 vector E plus vector P. Now speak reverse. Wherever you find epsilon 0 vector E plus vector P, you may replace it by symbol vector capital D. So replace this by symbol vector capital D dot vector ds, and that equals to q. Now this last step you can see here, correct? In the textbook they have given Gauss law for dielectric medium in this format. How to get this format I have shown to you. Got it?